Hello everyone, welcome to another edition of SaaS Engineering. After a very ill-deserved break, uh, I know it happens a little bit irregularly, but we have a very interesting talk today by Ashu, who's the CTO of Clarisights. So he's going to be talking about Mozek, which is I'll let him speak about it in detail. But Ashu was earlier CTO at Advice, and he was at Meta working on HPS. Is that right, Ashu? So yeah, please tell us about Mozek, Ashu. Take it away.
All right. Thanks, Siva, for the introduction. And since Siva has already introduced me, I'll jump right into Mozek. So this talk is about Mozek, which literally translates into brain. Mozek is a Czech word, and we basically use that word because Mozek is a system that we're building to kind of manage a lot of things at Clarisights, which a brain does. So we'll go deeper into it, how it's supposed to do that. Before we go into Mozek, I think it's important to talk about what Clarisights is, to basically introduce the use case first. What is it that we're trying to solve? So Clarisights basically is a SaaS platform which turns this into this. Basically, what it does is that it on the left side, what you can see is that there are a bunch of sources of data: Facebook, Google. There are email. You can see Gmail icon there also. So basically, our customers give us data from different sources through emails, through APIs. We can get the data, which is their reporting data for the ads that they run on these platforms. For example, people run ads on Facebook. So from the API that Facebook provides for fetching that data, the customers will provide access to their accounts and we'll be able to pull that data. And through some sort of magic, basically, well, that's what the customers have called us literally, that, okay, there is some magic happening behind the scenes, but there is a lot of engineering that goes into it. We actually turn it into what you see on the right side. Customers can actually analyze their spends, their revenues, the kind of transactions that are happening, what are the aggregate numbers, what are the granular numbers. For example, if you see on the right-hand side, you can see some images of pizzas and burgers, right? So customers can actually see, like, okay, if there was an ad that was shown which had an image of a pizza, how much did I actually spend on that particular ad? How much revenue did I actually get from that ad? All of that Clarisights does pretty much automatically without much configuration. So Clarisights is a SaaS platform, as I already introduced. It automatically integrates, processes, and visualizes all your data from marketing, analytical, and attribution sources. That's how you actually get the revenue also. Then it is usually targeted towards sophisticated marketing teams. For example, customers which are really, really large, they operate across multiple countries, they are really data-driven. For those kind of teams, Clarisights makes sense. And we have customers like Delivery Hero, Uber, About You, HelloFresh. There are large enterprises that use Clarisights day in and day out. So it's a single vertical solution to solve three problems. One is API integration to these data sources that I was just talking about. Then data transformation and enrichment. Basically, you can look at data on different axes. You can actually extract business-specific dimensions out of the data. And you can actually do interactive analytics and visualization on this data. What I mean by interactive analytics is that you can basically drill down into the data. You can slice and dice into the data as and when you're looking at it. You don't have to run hour-long queries to actually generate insights. You can basically do a click on the UI and you'll get your result within a few seconds. So to introduce the scale, or rather the complexity of the problem, this is a very, very high-level overview of what kind of granularity of the data that we're dealing with. So this is for a single customer. Let's take an example of any customer that I mentioned, there, Uber or Delivery Hero. You'll have more than 100 different data sources. These data sources could be API-driven, or it could be data coming from their custom databases like BigQuery or CSVs or Parquet files. More than 100 data sources. Then for each data source, you can have multiple sub data sources. Basically, something like an account, that's what Google or Facebook calls it. These are different units of authorization through which you can actually pull data. So a single customer can actually end up having thousands of accounts. Then usually these data sources actually come with a hierarchy also. So data can actually be pulled in from different endpoints for different hierarchies. As you see on Facebook, you can see an ad, but there is a lot of hierarchy on top of it also to control different parameters of an ad. So for example, an ad group or a campaign, that's also something there. So there are more than 4 levels per account usually for a data source. Then the data is also of 2 different types. You can have metrics, which are numbers, and you can have dimensions, which are basically attributes or strings associated with the data. Then metrics also can actually be different types. For example, the report that I just showed you in the screenshot, I was talking about costs. For example, how much you actually spent on the ads, and then there are conversions also. How much, for example, how many people clicked on the ad, or how much revenue did you actually get from the ad. So there are different kinds of metrics that can also be pulled, and these are independent of each other. They can be pulled independently, and each metric, obviously, then it's a time series data. Usually, most data sources will provide data on a date granularity, and every day we end up pulling 30 to 60 days worth of data, because this data keeps changing. Like Facebook and Google, what they will do is that they will do reattribution of the data. So what they will do is that even for last 30 days of data, the numbers can keep getting updated. So what we have to do is we have to keep pulling this data again and again and again for up to from last 30 days to up to 60 days of data for most data sources. So this is basically what I just described, hundreds of different data sources. There are several attributes like data source, account, level, date, type of data, metrics type, all of that. Then data also flows through different stages inside our system. This is something that was not covered in that diagram. For example, the same piece of data can actually take different shapes based on the use case inside our system. So that's also a different granularity in terms of pipelines. Basically, we have to run different pipelines to actually transform the data into different shapes. Then there is metrics and dimension data that goes into different databases, for example. So that's an example of this same data actually ending up in different shapes because they go to different databases. And conceptually, if you actually just do the math based on the number that I just gave, and you just aggregate it across all the customers that we currently have, you actually end up running more than 10 million pipelines conceptually every day. Obviously, this is not the exact number of pipelines that we actually run, because the systems that we currently use, they are not scalable to that number. They can't actually schedule and run greater than 10 million pipelines every day. So I'll discuss that also, how we are dealing with that problem. But conceptually, there are more than 10 million independent pipelines that we actually run every day. For these pipelines, there are different knobs also to turn for each attribute. For example, the data for last 7 days, it changes more frequently than the last 30 days of data. So what this means is that we need to actually pull the last 7 days worth of data again and again more frequently as compared to last 30 days worth of data. Then certain levels, for example, campaigns might have a certain type of metric that is available, but ad groups might not actually. So there are different configurations for different customers, the kind of data that we can even pull for different customers. Then different accounts also get data at different times of the day. For example, there is an account that is in US time zone, and then there is an account that is in Singapore time zone. They will actually get their data at very different times of the day from the place where, like, let's say if you use UTC as a reference point, right? The day in Singapore starts much earlier as compared to the day in US. So you will actually get the data for a particular date at very different timestamps. You cannot pull all the data together for a particular customer. And given the kind of customer that we have, for example, Uber, which is present globally, we actually have accounts for which data actually comes from so many different time zones. Then there are different kinds of knobs that can be adjusted only at runtime. For example, some APIs will have rate limits. Twitter, Snapchat, Facebook, they will each have their own rate limits. So you can't just throw API requests at those channels and they're not just going to reply. You have to make sure that you are only making a certain number of requests at a particular rate. So that means there are runtime adjustments that also need to happen. The system needs to adjust the number of requests that it is sending constantly. So with that, a different way to put it is this, that there are different kinds of workloads. They are overlapping in the sense that if you see the first example, 7 days of data and 30 days of data, there are 2 different pipelines that need to run for each of them. So they are overlapping in some sense. 30 days contains the 7 days thing also. There are conflicting pipelines also. Like the data could actually be changing from different pipelines for the same tables or same outputs. Basically, you can't be running those pipelines together, otherwise there will be conflicts. There are dependent workloads and there are independent workloads. Then there are concepts like manual runs, like someone might actually want to backfill a certain piece of data manually. So all of those different use cases actually exist internally in the system. And the important part is that some of these stages through which the data passes, there are external factors also. For example, we are pulling data from APIs. It's quite possible that Facebook's API is down today, or it's not behaving at the same performance as it was doing yesterday, right? So there are external failure modes and there are internal failure modes also. Like the system internally might be doing some business logic, which might be buggy or it might be susceptible to systemic failures. So all of these different problems exist through which we actually have to kind of make our way through to actually make sure that we are able to orchestrate data processing at Clarisights. So just before I dive into Mozek, a very quick overview of how we were doing it earlier. So very first version was Kubernetes cron jobs. It basically directly translated from the notion of cron jobs that we used in the, like literally on day one of Clarisights. So it's like you give a schedule and you basically get a container that runs at that schedule. So what we used to do was that, okay, for each data source, we'll run a separate cron job. Inside a cron job, we'll run separate threads for each customer. And that was literally it. And that worked for some time until we were at a certain scale or certain number of customers. But as things scaled up, and it was really hard to maintain visibility and maintainability with this kind of setup. So we wrote certain extensions on top of it. For example, we wrote a Ruby DSL to define cron jobs rather than actually writing the whole big Kubernetes YAML. We tried to do somewhat intelligent resource allocation so that we don't allocate the same set of resources to all containers that we run. Obviously, these workloads are not all same in the amount of processing that they're doing. Then we tried to do tenant grouping to isolate heavy customers. So it worked for some time, but obviously there are a lot of problems here. With just cron jobs, you don't get the visibility, you don't get the control that you want. So we moved on to a more intelligent system. We moved on to Airflow, where we could register DAGs to specify dependencies, basically steps of execution. That's something that we could do. What we would do was that we would query, we would basically queue multiple runs in Airflow with the same set of arguments for a specific DAG. For example, let's say I want to run a pipeline for Facebook for different customers. So I would specify something like this, like there are different tenant IDs. They would actually correspond to accounts that I was talking about. And I would run them in a single DAG run. I could have run them separately also. For example, 7221 could have run in a specific instance, and then 7222 could have run in a different instance. But then, as I said, we are running more than 10 billion pipelines. Airflow needs to be able to schedule that many pipelines in a day. And what we have seen is that Airflow does a lot more work in its critical section, and it's not able to scale to this number when we run these things in different jobs. There are other considerations also. For example, we are using Kubernetes executors, so spawning up a new container for each of those 10 billion pipelines, that was also a problem. So what we ended up doing was that we'll batch them together. Obviously, this creates its own set of problems that I will discuss later, but this is how we basically got around the 10 million number, that we could reduce it by a factor of, let's say, 10x or 20x, while we are actually running it on Airflow. We ended up writing a service wrapper also to introduce concepts of priorities, queuing, throttling, all of that we did on top of Airflow. Now, what are the problems with this setup? There were certain problems that we identified. One, the biggest problem was that there is no dynamic adjustment of resources. Let's say if I'm going to miss an SLA, a customer wants data by 10 a.m. in the morning, and I'm about to miss that. For some systemic problem, I was not able to schedule the work right now or just before 10 a.m. Do my resources automatically adjust to actually make it run faster? Do my scheduling decisions change when this happens? That was really, really hard to implement in a Airflow-based system. Plus, the scheduling is very static in the sense that if I schedule a DAG, the whole DAG runs. It's quite possible that I actually wanted to run only a particular stage in the DAG for whatever reason. It could be a business constraint that the customer only wants a specific type of data. So all of that required adding more and more business logic into our code rather than Airflow giving a system to handle it gracefully. Another big problem is missed schedule. So this is a common problem with any scheduler. Airflow is not an exception. Plus, cron jobs have even a bigger problem. So let's say the system is down at a particular time. Does it know that a schedule is missed? Let's say I bring the system back up. How long will it take to actually rerun the thing that was actually missed at a particular schedule? When you have a custom wrapper on top of it, you have now two brains. Basically, the queuing system that we have written and the one that Airflow has, now they are also out of sync. How do you make sure that the missed schedules are actually not really missed? You can actually rerun them as soon as possible. The checkpointing is also hard. So let's say if you are running multiple stages on your data, then how do you make sure that if you have done a certain part of work, you don't repeat it if something fails? You only do whatever you've done partially. To be able to get around this problem, we have to build this logic inside our own code base rather than the orchestration layer handling it for us. So this is also hard in a generic system like Airflow. Overlapping and dependent workloads, also it's really hard to coordinate. You have to do distributed locking to make sure that two things don't run together. And even if you do locking, like how long do you wait before you release a lock? Is it possible? It's possible that you might actually starve other things that are conflicting. So these are also problems when you are running things as a pipeline. Isolation is also hard. Remember the example I just gave before this slide? We are running things in batches. This causes a problem of noisy neighbor. Let's say one account that we are running in a particular batch that has a problem. How can we guarantee that it doesn't affect every other account that are running in the same batch? Maybe it will out that particular container. How do we protect the other ones that are running in the same container? So these problems actually emerge from some fundamental notions about the orchestrators that we have been using so far. The generic systems like Airflow, they deal in the concepts like schedules, DAGs, pipelines, and tasks. And the problem is that the business doesn't operate on these attributes, right? Any business attributes are going to be different. Like for example, for us, it will be customer ID, it will be data source, it will be account ID. Those are the kind of things on which we want to actually schedule. Those are the kind of attributes on which we want to take scheduling decisions rather than the pipelines, DAGs, and like fixed periods or tasks, right? So once we add that constraint in, the number of tasks that we need to run, that number is really, really large. As I said, 10 million, right? So that's something that Airflow has to be able to schedule. And this is with a small set of customers. What if we increase the number of customers by 100x? Will that also scale in this scenario? So that's a big problem in generic systems. So to get around these problems, we have already built layers and layers on top of existing systems like Airflow. And those layers have served the purpose so far, but we have still compromised on desired attributes like visibility, scale, and efficiency. Remember, I was talking about the redundant work, overlapping work. How do we actually make sure that it's all deduplicated automatically? None of that actually happens unless we actually go and change code for every single data source that we're integrating. Let's say Facebook, Google, all of them have to support deduplicating work, automatically detecting that there's a conflicting piece of work that is running. Ideally, your orchestrator has to be able to provide you the constructs so that you can easily handle it without having to build it inside your business code. So with all that in mind, we basically went after tackling this problem from the fundamentals. So one thing is that in orchestration systems, usually you will have two high-level components. One is a decision engine, and then there is an execution engine. So Mozek what we're thinking of is that we are going to rewrite the decision engine, because the current decision engines are basically very, very different fundamental philosophy from what we want to actually do. And the execution engine is something that we can just use. For example, if we want to run a particular set of tasks, we can still just offload it to some existing execution engine. But as long as the decision engine is smart enough to make sure all of these semantics are provided for, then our problem is solved. So this is exactly what Mozek is. It's a homegrown decision engine that we have written for orchestrating data pipelines at Clarisights to solve all the problems that I was mentioning earlier. So what is the underlying philosophy of Mozek? So just before I actually go into the philosophy, I just want to throw one line there. To actually solve correctly recording the triggers and periods that usually orchestration engines use, we have invented queues. Basically, let's say some customer event fired or some particular schedule got triggered. How do I make sure that I actually don't miss it if the system is down? So what we have done is that, okay, I'm going to queue it in Kafka or in some, I don't know, RabbitMQ, some queue which doesn't lose that event. And I'm going to read it back from there. So the world has kind of tried to solve or hack around this problem by using more and more resilient systems. But the point is that it is still very, very imperative in the sense that these systems are still prone to failures. It can still happen that your queue is also down, or your queue actually was not able to respond in time and you basically gave up. So the problem is that scheduling, we have been looking at it as a trigger or a period-based decision, but it is not really that. It is a state-based decision. I'll give an analogy. Let's say you drive to office by I don't know, some rented car, or maybe you take a cab to your office, right? And for some reason that service is not available today, right? And you really, really have to go to the office. You have to, or maybe you have to really go to the hospital, wherever, some really, really important place. So it's a very, very common scenario. That's why you decide to buy a car, because you want the flexibility to actually leave your home at any point of time, whenever you want it, right? Let's say you face this problem today, you decide to buy the car today. Tomorrow, the cab service has resumed. The problem has gone away, right? Not really. The problem is not that of schedule, that you face the problem today and you have to immediately solve it. It is still going to happen maybe 7 days from now or 1 month from now. So you're still going to buy the car because the problem still exists. So the reason you actually decided to buy the car was not because of something that happened today. That was not the trigger. You wanted to change the state of your world. You basically wanted to have the flexibility to actually be able to go out of your home at any point of time. So whenever we are talking about orchestration systems, they are not really driven by something like, okay, run something at 6 a.m. No. What we're actually trying to say is that I want my state of the data to change in a certain way by 6 a.m. That is the decision. If the state is already correct, then I don't care. I don't want it to be run at 6 a.m., right? So this is the underlying philosophy that Mozek has adopted, that instead of looking at it from a period or a trigger-based system, what we are going to look at it is that we are going to look at the state of the data. Does the data actually say that something needs to happen? Once you actually put that idea in, you're not really talking about things every 1 hour or at 6 a.m. You're not talking about those kind of questions. You can actually ask the question about your data at any point of time. You can say, is my data in an undesired state? If it is an undesired state, then I'm going to do some work. So yeah, this is literally the philosophy that Mozek takes. That amount of work done is, first of all, work is done only if you want to change from an undesired state to a desired state. And the amount of work done is never more than the work required to literally just change that state. So these are the two important fundamental concepts behind Mozek design. So I'm going to pause here. Does anyone have any questions so far on the basic philosophy before I actually go into the components of Mozek? All right. Okay. So we'll take the questions at the end. Yeah.
Sorry, quick question. You said you're not looking schedule as a trigger, but more of a state. Would you mind giving an example?
So I gave the analogy from the real world, but I'll give you the example from the data perspective also. I'll have to probably skip a few slides.
Okay, I'll wait then. I'll wait otherwise.
Okay, all right. So I'll give the example at a later point in time. There are examples of rules that we use to actually define those state-based decisions also.
Yeah, sure.
So, but before I go there, there are 2-3 concepts that I need to introduce, which are fundamental components of Mozek. A split is the smallest unit of data in our system on which these business constraints can be applied. So this is not the smallest amount of work. This is not that whole pipeline-based system that we are used to. This is just the state of the data. What is the smallest piece of data on which we can ask the question, is it in an undesired state or is it in a desired state? That is what a split is. So an example is data source is Facebook, account is some XYZ, level campaign, basically all these attributes that I introduced earlier, right? You can pick a combination of these attributes and you can ask a question. Is this thing in a desired state? Is this, for example, does it have the latest data? Something like that. Those kind of questions you can ask. And then basically a split is uniquely identifiable through the set of attributes that you use to actually query the split itself. So what that means is that you are automatically deduplicating your data across, let's say if you want to do multiple runs, there's already a unique identity of the data across those runs also, because it is defined by the attributes associated with that data. Then there are DAGs, obviously, because eventually you want to translate it into work also. So you have to define a set of steps that will be required if a particular split is in an undesired state. Then you have to define a graph of dependencies, like what needs to happen. So an example is, this is a simplified version. This is a JSON version of the DAG, a node in a DAG that we have. What it is basically saying is that if you see here, ID, it's just the ID of the node. Then there are a bunch of arguments associated with splits. What it's saying is that the split, which corresponds to the data source AdWords, and accounts will be computed at runtime. Universe of is just a placeholder function that I have added here just for the purpose of this presentation. Then your stage is reports. Level is again computed at runtime. There is the only possible values for report type is stats, all of that, right? So a split that is identified by these set of attributes, it actually depends on a split which is identified by another node, which is core. So a DAG is basically whenever I run the reports node, it will be after the core node. So anything that happens for core, that has to kind of trickle down to reports also in terms of execution. Here, we are not talking about decision. The decision is still declarative. This is when you have already decided to run tasks corresponding to a certain set of splits. Then you are going to kind of take this decision. Okay, these are the dependent splits. I'm going to kind of make sure that they also get updated. The way to look at it would be, let's say the API from which you are fetching the data. You have basically kind of decided that the API is giving you new data. For whatever reason, you have decided that my data is in undesired state, so I'm going to fetch new data. But there are two different databases through which this data needs to go through, right? So there will be another node for the second stage of this processing, which will get automatically picked up once a particular split is picked up. So all the dependent splits are going to get automatically picked up. I think there was a question. So would core also have same split arcs? Core will not necessarily have same split arcs, but there will be some overlapping set. Anything that is not overlapping, for that we'll pick the whole universe. So that's why this whole universe thing actually exists. So let's say there is the core node does not have a concept of report type, right? But it might have everything else. So basically, this will actually get dropped, but everything else that is overlapping at channel, account, stage, and date for the core node, they will be run, basically all the splits with that particular value. So let's say there is a split for this reports node that says that at channel is AdWords, account is some account ID 1, and stage is reports, level is, let's say, campaign. and report type is already defined here, and date is, let's say, January 1, right? This gets triggered only after some core split was also triggered, and that split was identified by some overlapping attributes here. Let's say in that case would have been ad channel would have been AdWords, account would have been account ID 1 again, but your level would be and your level would be campaign. Your report type may or may not exist, but your stage would be core there. So what that means is that you will have certain attributes which are different, but everything else that is overlapping here that will automatically be picked up. It's think of it like as a prefix matching. So let's say you have certain splits defined by a certain set of attributes, and any prefix you have picked up for a particular node, all the splits that have the same prefix for any dependent node, they will also be considered as immediately dependent splits for that particular split. Date is relative. How does that work? So date here, this is also a universe thing here, that this is the maximum set of dates that we'll pick up for this particular DAG, and date is relative from today. The way it will work is that when we are generating splits, we are actually going to generate one split for each date, and the splits are actually persisted to the database. So let's say tomorrow also the same date is picked up, right? The split already exists. The only thing that will change is that the state of the split has changed now that this split is in an undesired state. So I think the DAG thing is going to be a little bit confusing until I introduce the rules part. So Siva, I'll request you to hold off your questions for a little bit. I think things will become a lot more clear once I introduce the rules. All right, so I'll just get the usual components out of the way. That there is a scheduler, definitely. It is a central component that coordinates with all the other components. It transforms splits into tasks. Split is a piece of data, but task is an actual unit of work that is actually happening. It is quite possible multiple splits are running on the same task also. That's an execution decision. Mozek is not concerned with that immediately. This is something that can be decided based on things like rate limits and other things that basically your resource decisions that can define how the mapping of splits to tasks is happening. But at the end of the day, any splits that a particular task is running, if a task completes, all the splits are actually considered as completed also. Then there is a task tracker. Obviously, this tracks the life cycle of the tasks. There is an execution engine. It's basically a set of, it's a dynamically scalable cluster of hot workers. Basically, the workers are just there to pick up work. So you don't have to spawn a new worker when a task becomes available. But it is scalable also. You can add new workers on the fly. Let's say if there are too many tasks in the queue, so then yes, you can add more workers. Then there is a central component, which is metadata. Obviously, this is all the metadata that we have to store regarding splits and tasks. This is what gets stored in the metadata system. So now to come to the declarative component. This is the most important part from the philosophy of Mozek, that we have a rule engine. And this rule engine basically is going to specify business constraints that dictate the SLAs associated with the data. And you can have multiple rules for each customer. So let me give an example of a rule here. Usually for pipelines, you would specify run every 6 hours. But this is not what we would specify in Mozek. What we would actually specify as a rule would be that you would say that for a certain piece of data, which is identified by these split attributes that I was talking about earlier, the data is never more stale than 6 hours at any point of time. So what this means is that, yes, the period is automatically captured. If something ran at 1 a.m., then it has to run at 7 a.m. also. But the point is that if there was a missed schedule, you are not going to wait another 6 hours to pick it up. You are going to immediately see that, oh, data is more stale than 6 hours. So I'm again going to pick up as soon as my Mozek system comes back alive. Another example of a rule is, let's say you say that run at 10 a.m. every day. No, you want to say data is newer than 10 a.m. for today. Then a node 2 in a DAG says that you need to kind of run after node 1. It's the dependency that I was showing earlier in the DAG. Then how that would be modeled in the form of rules is that what you're going to kind of say is that data represented by node 2 is always newer than node 1. This is again an implicit rule which comes from the definition of the DAG itself. If node 2 depends on node 1, then Mozek already knows that this is a rule that is already there, that every piece of data that is dependent, that is kind of represented by node 2, has to be newer version than the data represented by node 1. Then manual runs, again, you're basically saying is that data is newer than a certain timestamp or a version. Basically, when you say that, okay, I want to do a manual run now, or at a particular timestamp, I want to do a manual run, right? So what that means is that the rule will actually look like this, that the data is newer than that particular timestamp. That's all. So this is again a JSON representation of the rules that I was talking about, one of the example rules. This is not how it's actually written. It is stored in database as a proper set of columns and structures. But for showing here, I've kind of converted it into a JSON representation. So there are two important parts here. One is, if you see, let's first talk about the split attribute conditions and try to relate it to the DAG that I was showing earlier. What this rule is basically saying is that for these particular attributes where value is basically stage is equal to core, level is equal to campaign, and ad channel equal to adverts. For this particular, for all splits that are identified by this. So one thing I want to add here is that a split can actually have more than this number of attributes. So it's possible that this particular set of conditions will match more than one split. In fact, it should actually match more than one split. There might be a date component, there might be an account component, there might be other components, but anything that matches these set of conditions. For all of those splits, what we want to do is that the last scheduled time is never more than 6 hours ago. This is a way to specify this particular rule. I would say that you can ignore these execution context stars. These are basically fixed parameters that we can pass to the run itself, but the declarative part is basically here. That you can basically say that my data is never more than this many hours old. This is a way of saying this. Does this answer your question? I think it was Ram who was asking this, right?
Yeah, it answered. Thank you.
Okay. Seva, did your question also get answered? All right. Okay. So this is also, well, this is a very simplified representation of the architecture, but I'll just go through the steps very quickly just to make sure that it is clear what is happening. So we have a business database. This is outside Mozek, obviously. This is something that things are already there. There are a bunch of these attributes associated with business specific data. Mozek is just going to read all of these attributes and it's going to kind of create all the splits that are possible. This is async. This is happening. This is not happening in the critical path. So that's why it doesn't matter how many splits are there. You are not going to really block your scheduling decisions on those splits. You can just keep creating splits async as and when more and more attributes or more data keeps coming to your business DB. So you're going to create splits and register them into Mozek DB. Then there is a loop, there is a scheduler loop that runs. It basically reads all the splits. It reads them with rules filters. It already knows what are all the rules for a particular customer. So it's going to pass down all those filters to the DB. It's going to read all the splits that might be eligible for all the rules that are there in the database. It's going to again give it back to the rule engine and then get filtered splits. Why are there two parts of filtering? It's similar to what Spark also does. Like, for example, you can push down certain filters to a particular piece of, to a particular database or to a particular engine, but there might be certain rules which you can't actually push down. So there is a final level of filtering that needs to happen. Currently, we don't do this. Everything is pushed down, but it's quite possible that we might end up adding certain rules that we can't directly push to our metadata DB, which is currently Postgres actually. So it's possible that Postgres might not be supporting certain functions. So we might have to do it in the rule compute engine. Once you get the list of splits, it's as simple as just saying that, okay, schedule all the splits, tell the task tracker to kind of run the tasks on the execution engine and keep checking whether, okay, the tasks are complete or not. Once they're complete, you can notify the scheduler. Again, the notification is just a convenience thing because everything is tracked here in Mozek metadata DB. The scheduler can be down. Execution engine is running. It might have completed something. Scheduler can come back up. it can just check with the execution engine, okay, can you tell me whether the tasks are actually complete or not? So everything is state driven here. There are no triggers or notifications that it actually depends on. So these are some of the very, well, it might be obvious, it might not be obvious, but these are some of the very important advantages of the design. The most important thing is that there is no schedule. So obviously since there is no schedule, there is no missed schedule. You are never going to worry about things like, okay, did I actually run this at a particular time? While it sounds like a very small thing, this is the most important part of our system, actually, because we are running so many, like millions of pipelines, right? It's very easy to miss schedules. It happens left and right every day. And this is something which is a huge lifesaver for us in terms of design. Again, because we are only doing the amount of work that is necessary to change the undesired state, the checkpointing is automatic. We are only running things in splits, right? So you're recording the change in state of a split. You know that the split is up to date. Even if the system went down, it came back up, the change in the state is still recorded in the Mozek metadata DB, and then you don't have to do that work again. This is another very, very important piece. There are different like backfills, and remember those 30 days versus 7 days I was talking about. There are different pieces of workload that might be overlapping. The important part is that we are not starting out as pipelines. It's not like different jobs are running and then they're looking for deduplication or kind of removing conflicting work by taking distributed logs. There is no such thing happening. We are starting with data. So it is automatically deduplicated already. You don't even have to think about conflicting work because there is no conflicting work. Then the rules themselves, they are business rules. Basically, this is what customer wants. So we are not talking about things like run this at a particular time. Customer wants the data to be refreshed every 6 hours or basically at a particular time. So these are the rules that are like very close to English rules, which can be understood by business folks in the company also. There is another very important part here. If you really notice, all the scheduling decisions, the rules and everything, they are at the granularity level of a split. So what this means is that I can actually offload the work of kind of asking this question, whether the split needs to be scheduled or not, to different workers also. It is very, very highly parallelizable. I can basically throw n number of workers on the system and they can each answer, okay, does this split actually need to be scheduled or not, by applying those rules. And since the system is actually based on the concept of undesired state, it's really easy to ask the question, okay, at any point of time, I can just tell the customer, is any piece of data stale right now for you? So that's a very easy way of kind of telling the customer, is your data up to date or not? Also, this is a question that we get asked a lot of times, and we don't have a good answer right now. We can only tell that, okay, a job has completed or it has not completed. But what about like those 1,000 pieces of work that this particular job was doing? Maybe 999 of them are actually complete. Now we can actually tell that okay, only very small 0.1% of your data is not up to date, but everything else is up to date. Quickly going over tech stack, the most important part is the fact that we are taking a lot of decisions here, so we can't really be wrong. Correctness is very important. And a lot of things that we're doing, they're just transformations and list manipulations because we are dealing with splits, dependencies, lists of splits, those kind of things. So, and we also wanted it to be like really, really highly parallelizable. Just throw more resources if the number of customers increases. Sure, it might be slightly less efficient if we just throw more resources, but we can solve that problem separately. But it's not like we are going to be capped at a particular throughput. So with all of that in mind, we actually chose Elixir for this because Elixir has, well, it is functional. It has a very, very easy syntax to understand also for this particular use case. The other important part is that Elixir comes with green processes. So very, very lightweight threads that you can run, and you can run them over multiple machines also. So remember the part that I was talking about where you can kind of throw this work at multiple workers. That's super easy to do in a language like Elixir. The metadata that we have, currently the interface is defined, but it is chosen as pluggable. What that means is that we are using PostgreSQL right now. Tomorrow we can actually choose to use something else for storing metadata also. The execution engine, again, that is not really part of Mozek, so that's also kept pluggable. The only requirement is that we want to use hot workers. It's not like you have to spawn a new process for every new piece of work. That's too much latency. Our legacy code base that we have for doing a lot of computation, that is in Ruby. So we started with Sidekick, which provides hot workers for Ruby, but we have a bunch of like Scala code and other pieces of other kind of languages that are already there. So we are kind of working on implementing pluggable systems for pluggable execution engine for those languages also. So now what is the current state? So while I'm talking about it, this is like literally bleeding edge at Clarisights. It's not even cutting edge. What that means is that this is currently going live for the first set of customers. We are currently testing for the first set of customers, and it's quite possible that there are loopholes in the implementation. The design has already been verified through POCs, so I'm hoping that is going to stand the test of time, but it is quite possible that the implementation needs a lot more work to actually make it scale. Yeah, so that's pretty much it I have on Mozek. Any questions? I'm happy to answer.
So one question, in the entire discussion, I didn't follow, what is the pipeline? Is that one data source, one account? Is that what you call a pipeline, or?
So when I was talking about 10 million pipelines, right? So there, the important part is that there are things which you can run independently. So let's say one data source, one account, one report type, one date also. You could potentially run that independently of the other date, right? Okay. And so conceptually, that is also a pipeline. We don't run 10 million pipelines physically right now. That's why I said we are able to reduce this by a factor of 20x, 30x by actually running them together. We club together multiple dates, obviously. But the important part is that we want to have the capability of running them separately also, which was lacking because of the limitations of existing orchestration systems. With Mozek, we have that capability now. We can potentially run them separately also.
See, actually, since you have accounts concept, this third-party API restrict you to request by accounts, right? So yes, you need to have that separation at account level, if not at the date level, right? If
exactly.
Not,
yeah, that needs to happen.
Okay, yeah. Is that right? What I said?
Yes, not, that is definitely there. Yeah.
Yeah. Okay.
Yeah, but the date separation is still needed because the data goes through multiple stages in the system. So even if the API thinks it's quite possible that, for example, we have seen for certain channels, the API limits are so low, the rate limits are so low, you cannot really do multiple requests for the same account at the same time. So obviously we end up doing one request or maybe 10 requests at a time for a particular account. But once the data is pulled in, there is still a lot of logic that goes into the system, and that all can be done in parallel for different dates, right? So instead of running it in different threads for each data source, kind of making that logic as part of the business code, now the important part is that the orchestrator itself is kind of giving us that capability, and it can automatically kind of merge those dates also. If it deems the resources are low, I can run two dates together in a single task. That's also there. So that flexibility is there downstream also. So but yes, you are right. The accounts have to be pulled separately. Most APIs won't allow you to pull data for two accounts at the same time.
Yeah. So in the beginning, you touched upon a very interesting concept, throwing more resources for a particular particular account, if the account is insanely big, or if it's a priority customer or something like that. In this design what you presented, I was looking for that component, that piece, is that addressed, is that available at this point, or
so currently, if you look at the rule, actually this is a very important and interesting question that you have asked. So the rule that we have, right here, we are only talking about scheduling, right? The data needs to update every 6 hours, right? But it is quite possible that the update itself is taking more than 6 hours. The actual run, right? What is Mozek going to do in that scenario, right? So because we are running things as splits, what the design actually addresses, and the implementation also, is that it can decide to run multiple, more than one split in parallel, right? It can decide, let's say I'm going to throw 100 workers for this particular customer right now, rather than doing it only on 10 workers, that I do generally. So all of that is there based on the SLA. So we have a concept of SLA in the system also. What you can define is that, so there is an implicit SLA here, which says that every 6 hours, right? So you have to finish within 6 hours. But you can still define an SLA, okay, my data needs to be updated within 3 hours also. And as and when it is nearing the SLA, it can decide to choose to kind of throw more workers at the problem.
Thank you. Yeah, I mean, I can ask one more question. I mean, since you guys are downloading a lot of data, like, the one challenge which comes is the data validation, right? Do you actually make sure that, although the data API execution is successful, right? And how do you make sure that data actually, got downloaded into the system? Do you have any, and how do you feed that information back to your Mozek system, in order to ensure there is a retry or something like that?
Yeah, so there are two aspects of this. One is that the data itself, let's say there is a problem downloading the data, like for example, an error was encountered, or basically it is taking too long, so then the timeout was triggered, something like that, right? So that is already part of the design. Those are considered as systemic failures. What we have done is basically we have kind of identified the class of errors into two broad buckets. There are systemic problems and there are user, or rather logical problems. The systemic problems automatically get addressed by Mozek. If you see the beauty of this design, that's something that I did not cover here. There is no need for a retry. There is no concept of a retry in the system, because again, you are looking at the state of the data. If there was an error in the last tick, the next tick is definitely going to kind of pick it up that, okay, this thing was actually ended up in an error. I'm just going to pick it up. This is not refreshed. This is undesired state, right? So there is not even a retry loop. But that is only for systemic problems. But there can be logical problems which are either identifiable by Mozek. For example, an authorization problem happened. Credentials are wrong. On that, Mozek is going to actually just raise an alert and give up. And it's going to, and then manual intervention is required to kind of mark that those set of splits again ready for processing once credentials are fixed. But there is another class of errors as part of these logical errors, which is the code is wrong. The data is wrong, right? We pulled the data in a different way. Maybe we pulled partial data in our code. That is not something that is addressed by Mozek design. We have different systems to check for that. We have something called a data sanity checker, which you can kind of download aggregate numbers from the API and compare it to aggregate numbers in your system. So that's something that we do. And that is part of a DAG in the system. Like this runs as a last step in your execution process. But this is not something that Mozek design itself can address, because this is outside the scope of Mozek. Like this is just code that you've written to process data.
Okay.
Yeah, but just to add to that, what we have seen is that at least so far, 95% of the problems are actually systemic problems, because these are all APIs, right? They just keep misbehaving day in, day out, left and right. Yeah. So we are hoping to kind of solve those 95% of the problems by this system. And then the remaining 5%, we have to improve the sanity checkers that we are talking about. Maybe it just needs to become smarter and more granular, that it can actually pick up things which are even at a lower level, not just an aggregate number.
Yeah, I mean, as I said, like, since you're dealing with a lot of third-party APIs, they are very crazy, right? Sometimes the API execution is successful, but it doesn't return any data. But whereas, like, you are accepting the data, right? In this case, like, you have to feed that information back to your, like, generate some kind of splitters and, store the split data into database, and the scheduler should pick it up, right? So that's
so that is there. So that high level check is there because we have a sanity checker which runs at the end, right? So it is going to do that check whether the data that is expected from the API, that is actually what is stored in the system. But if the API lies again, let's say when you're doing the sanity check, again the API gives you wrong data, you can't do much. Like you can't really, how would you distinguish that the data is actually wrong? Then what you need is more intelligent system, something like an anomaly detection, that, okay, yesterday you got a number 100, today you are getting 0. So something is off today.
Right. Okay. Thank you, Ash.
All right. I guess there are no other questions.
Okay. Thanks everyone for attending this talk, and thanks Ashu. Very interesting talk about Mozek. And Dave will also share the video, hopefully by this weekend as well, for those who missed it. Thanks.
All right. Thank you. Thank you, Shiva.
Thanks. Bye.
Thank you, everyone. Bye-bye.